Okay, welcome back to physics. Let me get you thinking about moment of inertia, and we're going to have a couple of different ways that we can look at this and calculate it. So, importantly, maybe a good place to start is with Newton's second law. So we had Newton's second law for linear motion that said that force is equal to mass times linear acceleration. And when we replace those equivalents for linear acceleration with rotational equivalents, instead of force, I'll have torque. Instead of acceleration, I'll have angular acceleration. And I'm left with this quantity, which, we'll call moment of inertia. So anyway, we'll end up with an equation which says the sum of the torques is equal to the moment of inertia times angular acceleration. You may recall mass in a linear motion is really resistive force. So it resists acceleration. And we're going to think of moment of inertia as the equivalent for rotation. It's going to be that thing that resists angular acceleration. So it resists rotation. Sort of the laziness of rotation. We're going to have a couple of ways of calculating this, so let me get in two cases. So one case is going to be where we have axis of rotation, which is outside our object, so I can count the number of objects. Second case is where the axis of rotation is inside the object, in which case I'll have to either look it up or figure it out or do something to sort it through. So first case, so if I have someone that's swinging an object over their head, right, that the moment of inertia is going to be simply the product of the mass and the square of the distance. Right? So if I have more mass, it's harder to swing. If I have more distance, it's more difficult with the square of that. Right? So importantly, distance plays a bigger role than mass. If I have two objects that I want to swing in a circle, well, it's just twice as hard. Right? So I can simply add these together. So if I have, in the second case, I have some distance d, that I have two balls that I want to get swinging, I just add these together. It's the same idea as mass, right? If I have 2 kilograms, that's going to be twice as hard as 1 kilogram to get it to accelerate. And if I have 2 balls, it's going to be twice as hard as 1 ball. So pretty much the rule, though, is if you can count things, then you just add together individual MR squares. Right? So, for example, here I'm going to have this L-shaped object, and I've put it aligned it with an X and Y axis. So I'm going to have 1 kilogram that's on my Y axis, 2 kilogram mass that's on my X axis, and the 1 kilogram that's kind of off the axes. And these are connected by, I'm going to say, a massless bar. And if I want to get this to rotate about the X-axis, right? So my X-axis is my rotation point. So these two on top here are going to rotate underneath and around the x-axis, where I can figure out how much this is, right? So I have two masses that are not on the axis of rotation, so I can just mr squared and add these together. If I want to rotate it about the y-axis, well, now I've got different masses. So the 1 kilogram and now the 2 kilogram that are not on the y-axis are going to rotate about the y-axis. And I have a larger distance here, so notice I have a much larger moment of inertia. And the key point here is, is that the distance plays a bigger role than the mass. They're both important, but since distance gets squared, and that distance plays a bigger role. So this is one way we have of calculating a moment of inertia. So it's going to be mr squared and adding together however many objects I have. Right? The second way that I have is based off the idea that now I have an axis of rotation this inside. So I'm going to look at like a disc and a hoop, right? And the outside edge of my hoop, for instance, getting that mass to come all the way around the circle, it's going to have to travel further than mass that's on the inside, right? So it's hard to get that matter to go all the way around. And if I think about tangential velocity, right, that tangential velocity of mass that's on the outside of something that's rotating is going to be going faster than the tangential velocity of something that's on the inside. And you can think of velocity as kinetic energy, right? So it's going to be harder to get some mass that's further away to get it to rotate. So really what I want to look at is well, what is the distribution of mass? And if it has more mass that's further away, that's going to be harder to get to rotate, so I'll have a higher moment of inertia. And I'll have mass closer to the axis of rotation. It's going to be easier to get it to rotate, and I'm going to have a lower moment of inertia, a smaller moment of inertia. All right, so for a disc and a hoop, well, the question is which one has more mass further away from the center. Hopefully you recognize that the hoop has more mass further away, so I predict it's going to have a larger moment of inertia. And in fact, that when I look these up, I'll discover the disc has a moment of inertia of 1/2 mr squared, and a hoop is full mr squared. Essentially the same as having a bunch of balls that are being swung around in a circle around the axis of rotation. And there's interesting ways to look at this, right? So if I pull up a simulation, right, there is an effect that this has. So if I set a hoop and a disc at the top, even if they have the same mass and the same radius, right, and I let them run to the bottom, right, or I let them roll to the bottom, right, that the disc is easier to get it to rotate, so it gets to the bottom first. So it takes more of that energy going down the hill, more of that energy goes into getting that mass that's on the outside of the hoop rotating than getting the mass that's on closer to the axis of rotation rotating on the disc. Right? So there's an important functional difference, and they will behave differently due to this, right? So my disc is easier to get to rotate, and it's going to show up in some things like getting to the bottom of the hill first. Let me think about the hollow sphere versus a solid sphere, right? So if I have a hollow sphere, solid sphere, so I want to think about where is the mass distributed, and I want to figure out which one has a larger moment of inertia. I want to be asking the question which has a larger fraction of its mass further away. And hopefully you recognize that the solid ball is going to be very similar to my disc, my solid disc, where I'm going to have some mass that's quite close to the axis of rotation. And the hollow ball is more similar to my hoop, where I have more mass, more fraction of my mass that's further away. And so I want to think about it's going to be harder to get the hollow ball to rotate because there's a little more mass further away. And so I expect the moment of inertia for the hollow ball to be larger. So let's look at this. A hollow sphere, the moment of inertia is in fact 2/3 mr squared. And a solid sphere is 2/5. So a hollow sphere is a little over half, and a solid sphere is a little under half of mr squared. And again, there's a functional consequence of this. So, and if I look at my solid and hollow sphere, so here my hollow sphere is in green, right? It's going to be harder to get that to rotate. So it's going to be slower getting to the bottom, right? So more energy is going to go into rotating and less energy into going forward. So let's see what happens, right? So my solid sphere is quicker in getting to the bottom, and my solid sphere is quicker getting to the bottom. It's easier to get it to rotate. So this is the concept that I'm going to ask you to be able to stick with and be able to sort of predict roughly which one's going to be tougher to get to go. For the most part, we're not going to ask you to calculate these. That we'll ask you to either look it up or we'll provide you with enough information that you can figure it out. And so you'll be given oftentimes a table like this, which lists moment of inertias for different objects, and hopefully you recognize the reason for these being different. And for example, we could look at the thin rod, right? So my thin rod, this is calculated based upon the length in this case. So if I rotate it about the center, it's 1/12 ml squared. And if I rotate it about one end, it's 1/3 ml squared. So notice when I rotate about one end, I have more mass that's further away. And so it's going to be harder to get it to rotate. I expect to have a larger moment of inertia, and fortunately 1/3 is a larger value than 1/12, right? So it's a 4/12. So it is in fact represented in the moment of inertia as well. Anyway, I hope this helps you get your head around it. Again, you won't be asked in this class to calculate or derive a moment of inertia. That's Physics C. It's entertaining, and calculus is useful for that. But for this class, you'll be able to be asked to predict which one's going to be larger and be able to use them. Hope that helps. Talk to you soon. Bye.